This is for gas laws, and this is like, there's a math part in this one. Exam 4 is a take-home exam. It is scheduled to be given out on the 13th of November, okay? And then it gets turned back in before Thanksgiving break. So that way I can get it done, I can get it graded, and you will have 4 out of your 5 exams. You know what those grades will be, and then that can give you, I think the last day to drop without any penalty is like the 27th or the 26th of November. So that like gives you time to like look at what your overall average is. I do want you to sit and look at your grades, exams 1 through 3, as well as your mastering assignments. Look at those to see kind of like what things are maybe potentially pulling your grade up or pulling your grade down. If it's the mastering material, you've got to make sure that you get them done. Remember that you always have stuff due like on Sunday night after we cover. So like we're going to talk about gas laws today. So the gas laws are due this coming Sunday. It's a dynamic study module. And I did it this way because it helps to kind of get you to go over this material as soon as we finish covering it. Okay. So it's going to be, so you can just put, so this is going to end up being given out on November 13th. You'll have a week to do it and turn it back in. Okay, so the first part in chapter 7 is all about gases, what gases are, how they're different. And so this whole first part is what they call kind of like the kinetic molecular theory. So this is like the theory about how gases are different from solids and liquids. So one, remember that gases are far apart from each other. So basically they act as if the other gases around them have no effect. So like this little gas molecule is floating around and it almost never comes in contact with another gas molecules. Gas particles are they're in constant random motion. Their speed is very much dependent on their temperature. The higher the temperature, the faster the gas molecule is going to move. There are no attractive forces. So by that I mean gas molecules act like independent things. They're not affected by other gas molecules that might be near them. And they're moving, therefore they have this kinetic energy. As you increase the temperature, then you're going to increase the kinetic energy. You're going to increase this vibrational activity of gas molecules. Also, if you lower the temperature, then that has the opposite effect. So lowering the temperature decreases kinetic energy and decreases that vibrational motion that these molecules have. That's different from solids and liquids, because remember, solids and liquids touch each other. Solids are very rigidly arranged, tight, close together particles. Liquids flow past each other, so they do come in contact and they do have an effect on one another, but gases really don't. So this led to this understanding about gases and the way that they behave that is different from solids and liquids, and so that led to what they call the gas laws. So gas laws are based on a couple of things: temperature, volume, and pressure. So pressure is the first thing. So if you think about a container that contains molecules of gases, those gas molecules, we said, they're in constant motion. They're random motion, so they're not moving in a specific direction. They're just moving. When they hit the wall of the container, they bounce off. That force, when they bounce off the wall of the container, that's their pressure. So pressure is just the force that is exerted on the walls of a container by a gas. Couple of different ways we talk about units for pressure. We really are only going to talk about 2. We are going to talk about atmospheres. So ATM, when you see ATM, know that that is atmospheres. When you see ATM, remember that that's talking about a unit in pressure. The other unit that we are going to talk about is mmHg, millimeters of mercury. So when you see that, know that that is referring to pressure as well. Pounds per square inch, PSI, that's really when they talk about like tire pressure. We don't really use that in chemistry, so you don't really have to worry about that. And we're not really going to talk much about Pascal. so you don't have to worry about that as being a unit. But if you see ATM as a unit, then you gotta know that's pressure. If you see mmHg, know that that is a unit for pressure. So when coming up with what pressure was and a kind of unit value for it, they initially measured what they call air pressure. So if you are a person that is at sea level, which is pretty much us, I think Rocky Mount is like 15 feet above sea level, very, very close to sea level. All of eastern North Carolina is very, very close to sea level. When they talk about atmospheric pressure is really referring to the column of air that is above you. So this is air pressure. And at sea level, they made this like definitive description that this column of air is equal to 1 atmosphere. So that's how they came up with an atmosphere. It is just the amount of air that is above you, pressing down on you creates that force. So you tell me, if you live up in the mountains, do you have more pressure or less pressure above you?
More.
When looking at this picture, do you have more pressure or less pressure?
Less pressure.
Mm-hmm.
That's what makes your ears pop.
Mm-hmm. Because of that change in pressure. Okay, same thing like if you take off in a plane. The higher the pressure, the higher the elevation, the lower the pressure. So you see the difference. So up in the mountains, you will have less air pressure. Compared to at sea level. And when your ears pop, it's really because of airflow in and out through the eustachian tube or the tympanic, the auditory tube that helps to balance or equalize that pressure. But that's how they came up with 1 atmosphere. That's how they came up with like a generic amount, because like, you know how they do everything, like, well, what are we gonna make as an amount? So this is 1 atmosphere is the pressure of a column of air above you when you're at sea level. So if you're in the mountains, air pressure is less. So then they said, okay, well, 1 atmosphere is equal to what? So 1 atmosphere of pressure in millimeters of mercury is 760 millimeters of mercury. So those are equivalent. And we're really not going to do a lot of unit conversions, but just know that if you see millimeters of mercury, you're typically getting numbers that's like 700, 600, 800. So that, well, it's right here. So it's on the PowerPoint, but I'm just saying that those are actually equivalent. 1 atmosphere is equal to 760 millimeters of mercury. But when you see those unit values, just remember that those are pressure values. So in the 1600s, so this is like, we're talking 400 years ago, this is when a lot of gas law were developed, understood, experimented with, and it's really because they could use really simple equipment to be able to measure these things. So the first one is what they call Boyle's law, because Robert Boyle, he was an Irish chemist in the 1600s, and he looked at pressure and volume. So he kept temperature the same. So Boyle's law, temperature is constant. But he changed pressure and saw what it did to volume. So in this first one, so we'll say that here's our initial pressure and our initial volume. So if you look at the volume on this syringe, do you see that it's like 3 increments? So if we have this initial pressure, so the initial pressure, we'll say it's just equal to 1 atmosphere. And then the volume, the initial volume is 3 whatever units. So these could be milliliters, they could be liters. We'll just say it since it's a syringe, it looks like a little 3 milliliter syringe. So what he did is he measured the pressure change that happens when he doubled the pressure. So if he pushed down twice as hard on the little syringe, so now pressure here, so P2 is 2 atmospheres, doubling the volume. It went from 1 atmosphere to 2 atmospheres. What happens to the volume? If he doubled the pressure from 1 atmosphere to 2, the volume went down, right? To what? Maybe, so it was 3 initially, and that one looks kind of like
One.
more than 1. So all those little red balls are the gases, about 1.5. Can you see that? So when he doubled the pressure, the volume ended up being only 1.5 milliliters. So you said, oh, if I increase the pressure, I decrease the volume. So then he pushed down on the syringe 3 times as hard as it was initially. So in this last one, I ended up pushing 3 atmospheres of pressure on the end of the syringe. And now all those little gas molecules are squeezed into what? Into 1 milliliter.
That's the one I thought we was on.
So notice with this, he said, if I increase the pressure, the volume goes down, and they're relational. So if I have 1 atmosphere of pressure, my volume is 3. If I have 3 atmospheres of pressure, my volume is only 1. So as one goes up, the other goes down to keep themselves related. Same thing happens if I increase the volume, then I'm going to decrease the pressure. So he said that pressure and volume were inversely related. If one goes up, the other goes down. And Boyle's law is really best explained by talking about what happens when you breathe. So ventilation, breathing, just the physical act of inhaling and exhaling is a good example of Boyle's law. So the easiest way, I think, to describe it is just to do it with a little picture. So the top one, this is when you inhale. So you know when you inhale, the act of inhaling is called an active process. It is active because it involves muscle contraction. So in order to inhale, you have to have muscle contraction. So there's 2 groups of muscles that come into play. 2 groups of muscles that help to change the volume in the thoracic cavity. The first muscle is the biggest one. It's the diaphragm. So everybody knows the diaphragm is what separates your thoracic and abdominal pelvic cavity. It is a flat muscle. This muscle, when it's relaxed, is sort of like a bow. It sort of like curves upwards. So you can see the diaphragm right here. So above is the thoracic cavity containing the lungs and the heart. Below is going to be the abdominal pelvic cavity containing your stomach, liver, small intestine, large intestine. So when this muscle contracts, when muscles contract, they get shorter. So if this muscle is kind of like a dome, like this, when it contracts, it gets shorter, which means it's going to go down. So shortening is going to make it actually decrease or lower in terms of its position. So when the diaphragm contracts, it's going to move down. The other set of muscles are muscles between the ribs. Those muscles are called the intercostals. And the word inter means between and costals means rib. So remember, intercostals are between ribs. And these muscles, so there's like a little group of them, each one between each rib. When these contract, they pull your ribs up and out. And so you can kind of feel that when you do an inhale. You can feel your ribs like go up and out as you do an inhale. You can feel them drop in and down as you exhale. So the external intercostals, or just the intercostal muscles, they help to pull the ribs up and out. So notice that that is going to cause those ribs to go out, out, out. So this muscle contraction does what to the volume of the thoracic cavity? So if the diaphragm goes down, the ribs go up and out, then inside of your thoracic cavity, the volume goes what? Up or down? So if this goes, So when you inhale, this goes up, this goes down, so the volume inside goes up. So these two are going to cause an increase in the volume. So now the volume's like this. Instead of being like this, the volume comes up, the diaphragm drops down. I increase the volume. What's that going to do to the pressure inside? So we said if volume goes up, pressure goes down. So that is going to decrease the pressure inside of the thoracic cavity. Negative pressure acts as suction. So when the pressure goes down, that creates suction. The only way to balance the pressure is to allow air to move from the mouth into the trachea, down to the bronchi, and then to the lungs, and allows the lungs to then pull air in. So suction pulls air into the lungs. And it does it until the pressure rebalances. So like if you just do a normal inhale, then your diaphragm doesn't drop way down, it just drops down some. The ribs don't go way up, they just come up some, and you just pull in some air. But if you take a deep breath, then you really pull the ribs up and out, you really drop the diaphragm so the volume goes way up and the pressure goes way down, and that sucks more air in. So you can adjust how much air you pull in by changing the volume of the thoracic cavity. And you do that by contracting those muscles. So the lungs really are just like these spongy balloons. The lungs do not inflate on their own. The only reason that your lungs inflate is because air gets pulled in due to this pressure change. So now you're at the top of an inhale. Here, okay? And then you start the exhale. So an exhale is actually a passive process. It's passive because it occurs when muscles relax. When muscles relax, those same groups of muscles that pulled the thoracic cavity up and out now is going to allow the volume of the thoracic cavity to go down. So when the intercostals relax, the ribs begin to drop back in. When the diaphragm relaxes, then the muscle begins to go higher, becoming more of a curve, going back up. And so now, what does that do to the volume inside of the thoracic cavity?
Go low.
So now, my volume's going to go down. And so if volume goes down, what does that do to the pressure on the air inside of the thoracic cavity? Increases. Right? So if one goes up, the other goes down. If one goes down, the other goes up. So this causes the pressure to increase, and this acts as a force that pushes air out. So the volume of the thoracic cavity goes down, and the only way to allow that pressure to rebalance is to push air out, and it'll come out until the pressure balances again. So you can exhale a little, or you can exhale like you're blowing up a balloon, where you're really pushing air forcefully out. That just, the change in the volume is going to change the amount of pressure that pushes that air out. Once you get to this point, then you go back to the inhale. So inhaling increases the volume, decreases the pressure, sucks air in. Exhaling decreases the volume, increases the pressure, and that's what pushes air out. So that movement, as long as your lungs are nice spongy balloons, then you have no problems with this air movement. People that have pneumonia, people that have COPD, people that have asthma, all of those can restrict this airflow and cause respiratory distress, cause issues with being able to move that air. But for anybody that's got like healthy lung tissue, then this is like a constant thing. You breathe 12 to 18 times a minute. Typically, you don't even think about it. It's something that just automatically occurs. You really only notice it if it's a problem. Like if you have an asthma attack, then you really notice your breathing. Or if you have pneumonia and you feel like you can't take a deep breath, then you really notice your breathing. But otherwise, this is a great example of Boyle's law. So now we're going to do some calculating. Okay? So in this, if you're given a math problem that involves Boyle's law, one thing that you'll notice is that you'll notice that the temperature stays the same. So the temperature won't change, but the pressure and the volume will. And you're always going to be given 3 out of the 4 values. So the way the formula works is that the initial pressure times the initial volume is going to be equal to the final pressure times the final volume. So you can think of the initial pressure as P1. You can think of the final pressure or the initial volume as V1. So you can use VI, PI, or V1 and P1. You can think of the final pressure as that second pressure and the final volume as the second volume. So you can use 1s and 2s. Just think P1, V1, that's what you start with. P2 and V2 is what you end up with. So what if I know P1, V1, and P2, and I need to find V2? What do I have to do to this formula? So I got to get V2 all by itself on one side of the equation. So if I have P1 times V1 equals P2 times V2, and I want to get V2 all by itself, what do I have to move? I've got to move P2. Everybody remember this? So if I want V2 all by itself, I have to move P2. So to move P2 to the other side, I need to divide both sides by P2. So if I divide this side by P2 and this side by P2, what happens to the right side of the equation? P2 and P2 will cancel. So you see that? So you start with the equation, whatever I need to find, that's got to end up by itself. And so in this one, if I need to get V2 by itself, divide both sides by P2. If I needed to get P1 by itself, I would divide both sides by V1. Okay, so whatever I've got to get by itself, that means I've got to move the other units to the opposite side. So I find that it's easier to rearrange an equation than plug numbers in last. So in this one, and we'll walk through it, and then I'll let you practice one. So if a sample of gas changes from a volume of 82.3 liters to 26.5 liters, what is the initial pressure if the final pressure is 1,825 millimeters of mercury? So when I look at this, I see 2 units that have liters. Those units are what? Volume. So I know that this is a volume, and I know that this is a volume. The initial pressure is the final pressure. And so 1,825 millimeters of mercury, that's a what? That's a pressure. So if I see volume and pressure, then I know it's Boyle's law. So if I know it's volume and pressure, then I know that I'm going to need Boyle's law. So Boyle's law is P1 V1 is equal to P2 V2. Those are multiplied times each other. So now I need to identify, what do I know? So what is 82.3 liters? That is the initial volume. So that is V1. What is 26.5 liters? That is V2. What else do I know? What is 1,825 millimeters of mercury?
Pressure.
It's pressure. Which one? Is it P1 or P2?
1, 2.
You got to read through.
Oh, no, that's P2.
Because it's final, right? So this is P2. So I need to find P1. So especially as you start to practice these, I'm going to encourage you to sit down and like write, what do I know? What do I got to find? Just so that you don't get them mixed up, read through the question and identify what units do you know, which values are they, which is V1, which is V2, which is P1, which is P2, and then figure out what you want to find. Usually what you want to find is in the very first part of the second sentence or the second part of the phrase. So in this one, when I see what was the, then that tells me that's what I'm trying to find. So that's how I know the initial pressure. I need to find P1. So P1 times V1 equals P2 times V2. If I've got to get P1 all by itself, how do I move? What do I got to move? Got to divide both sides by V1. So divide by V1, divided by V1. So do you see that that's going to get P1 all by itself? And now I just plug the numbers in. So P2 is 1,825 millimeters of mercury. V2 is 26.5 liters, divided by V1, which is 82.3 liters. Then just do the math. 1825 times 26.5 divided by 82.3. I got 5876. 587.6 36695. Now notice in here, liters and liters will cancel, so my answer is going to be in millimeters of mercury. So 587.636695. Can I keep all of those? No. So the last thing to always do is go back to the measured units in the problem. How many significant figures in 82.3? 3. How many in 26.5? 3. How many in 1,825? 4. So that means that my answer needs to have 3. So the first 3 that I get to is the 5, 8, and the 7.
Go around it.
I'm just going to round to what? 588. 3 significant figures. Decimal place comes after that. 8. Okay? But you want to set it up each time. So in this, determine the given information, which means figure out what are the 3 units I know, what is the unit I want to find, then rearrange the formula to find the one that you want to find the unit you don't know, then go ahead and plug the numbers in, and then the last thing to always do is make sure that you check significant figures. And the best way to do that is to go to the problem itself and figure out how many significant figures in each of those units. Okay, so here's another one. So you try this one. Okay, so if the pressure of a sample of oxygen changes from 2.5 atmospheres to 6.4, what is 2.5 atmospheres?
Pressure.
That is pressure. Is it 1 or 2?
It's V1 and 2.
It's not V1, it is
P1.
P1. Atmosphere is pressure, so it's P1, and then 6.4 atmospheres is P2. Then what will the final volume be if the initial volume was 0.025 liters? So 0.025 liters is V1. So, and again, you can see what will the final volume be. So that's usually like the very second part of the phrase or the sentence is usually going to give you the, tell me what this one is, the unknown. Okay, so in filling this out, so P1 is 2.5 atmospheres, V1 is 0.025 liters, P2 is 6.4 atmospheres, and V2 is the one I don't know. So I write it out, V1 times P1 equals P2 times V2. I've got to get V2 by itself, so that means I got to divide both sides by P2. That moves P2 over to the other side. V2 is now all by itself, and then I just plug them in. To keep yourself from accidentally putting P1 in the P2 slot, my suggestion is just to write them out. Because if you write them out, then the odds are that you're going to keep them straight. So it should be 2.5 atmospheres times 0.025 liters, and then divide it by 6.4 atmospheres. So this should be the way that the math is set up. And I got 0.009765625 liters, yes? Okay, but I can't keep all of that. So the very last thing is, how many significant figures should my answer have? 2. 2.5, 2 significant figures, 6.4, 2 significant figures, 0.025, 2 significant figures. So all of those have 2 significant figures. So in this, remember those zeros out front don't count. I keep them, but they're not significant figures. So the 9 and the 7 are the first 2 significant figures. Next number's a 6, so what is that gonna do? It's gonna round it up. So it'll be 0.0098 liters is the answer. Okay, so not terrible. It's every single time it's the same, is you're gonna know 3 out of the 4. And you really just have to identify what each one is, solve for the one that's the unknown, plug the numbers into the problem, and then round when you get your answer. Charles's law is really the other one that we're gonna talk about. So Charles's law, he kept pressure the same. So he said, okay, if I have a container that can change shape, like a balloon, that can change shape, when temperature changes, volume will change on a gas. Because what did I say? When you increase the temperature, what happens to the movement of molecules? They move faster. So if they move faster, then they are going to need to take up more volume. So what Charles found that these are actually proportional. So if one goes up, the other goes up. If I have an increase in volume, I will have an increase in temperature. If I have a decrease in temperature, that will accompany a decrease in volume of a sample of gas. Only that'll work for a little while longer. If one goes up, the other goes up. If one goes down, the other goes down. And if you think about balloons, balloons follow this because balloons, they can change shape, their volume is free to change, and changing the temperature of the gas can change the volume of those samples. So my best example, I have 2 children. Now, granted, one of them's 34 and the other one's 31 now. Gosh. Okay, so they're in their 30s. But we had this rule when they were growing up, is that however their age was, they got that many balloons. So that if they were 9, they always got like 8 regular balloons and 1 Mylar balloon. So that would be their 9. So when they started getting into their teens, it started getting a little ridiculous. Like I was having to go out and get 15 balloons and 1 Mylar for the 16th birthday. And even when they were 18, the oldest one was like, I'm still getting my balloons, aren't I? You know, I'm like, you're 18 years old. Don't you think maybe you're a little old for that? No. Okay. But I can tell you that the oldest one is her birthday is the very end of August. So very end of August in Eastern North Carolina, hot as blazes, okay? So here I go, and where do you go if you have to get 15 balloons? You don't go to Harris Teeter, that's for sure. You go to the Dollar Tree, okay? Because you can get a balloon, well now it's $1.25 or $1.50, yeah. But when they were little, it was only $1. So I was like, yeah, I can swing 15 balloons for $15. I can do that. So I go off to the Dollar Tree. And so then the Dollar Tree, it's the one that and this was when I lived in Wilson. So in Wilson, it was the one like near the movie theater, like near the mall. So that is like just this big black asphalt parking lot. So I've got the mom van because I drove a minivan the entire time they were young. Okay, so I drove the mom van, I park. It is the end of August. It is heat index 110 degrees. I'm like, yeah, okay. We go in to go get the balloons. So I'm sitting there waiting, and when you have to blow up 15 balloons and only one person's doing it, it does take a while. And then you're also like, well, I need plates, and I need this, and so you end up doing like all of this other stuff too. So by the time I actually come out, I have my 15 balloons in hand. I have my little bag of stuff that is going to be part of the party favors and such. But when I get to my car is not 70 degrees anymore. Inside of my car, it's now 100. It's really hot because I've been in the dollar store trying to get all of these balloons blown up in the middle of the summer. So I like open the van door and I start smashing them all in and pushing them all into the back. Finally get them all in, shut the door, get in the car. Okay, turn on the car, start packing out, start driving home, and inevitably, what do I hear? A pop. Why? Because I took these balloons from a 70-degree store and I put them in a 100-degree car. So what happens when gas molecules heat? They move faster. So then what happens to the volume? Volume increases. When molecules move faster, they require more volume. Increase in temperature, increase their volume, and that's why they're already blown up to their maximum. So inevitably, I wouldn't get home without losing at least one. And I can tell you the very first time this happened, I was like, what was that? It like scared the tar out of me. But then it was like, I just know this is gonna happen. And by the time she was 16, I took the other one with me and I was like, you stay in the car, I'm leaving it running because we're not losing balloons this year. Because inevitably, because the other one, her birthday's in June, so it wasn't as hot. It wasn't as bad, but it was the older one. I was always losing balloons because balloons in a hot car increase temperature, increase volume, and the balloons would pop. Following Charles's law. Now the other thing though, Charles actually put into this, he said, but if I take a gas and I drop the temperature below 0 degrees Celsius, now my temperature begins to increase as a negative number. And then I can't do this proportion. So this required that gases be based on their temperature with absolute 0. So absolute 0 is a temperature scale. It's the same number value as Celsius, but it's called Kelvin. So that temperature scale with Kelvin, if you have 0 degrees Celsius, that is equal to 273 degrees Kelvin. Absolute 0 is the coldest temperature a molecule can get. And remember, temperature is a measure of the vibration of a molecule. So 0 degrees Kelvin is the temperature at which molecules stop vibrating. 0 degrees Kelvin is going to be equal to minus 273 degrees Celsius. If we put that in Fahrenheit, it's about minus 459 degrees Fahrenheit. That's how cold that is. Extremely cold, but that is in theory, and they actually have gotten freezers that are within a few degrees of minus 459 degrees Fahrenheit. Yes. because of course, like a scientist is like, well, we're gonna do that. Okay, so they haven't gotten it actually all the way down to 0 degrees Kelvin, but they've gotten it very close. And so these molecules are like barely moving. So 0 degrees Kelvin is the coldest possible temperature because you can't make something not move once it stops moving, right? So that's how they consider it absolute zero. So it's actually not difficult to go from Celsius to Kelvin. All you have to do is add or subtract 273. So if I have something that is 100 degrees Celsius and I want to know what it is in Kelvin, I just add 273. So to go from degrees Celsius to Kelvin, just add 273. If I have Kelvin, if I know my Kelvin value and I want to go to degrees Celsius, just take away 273. I don't have to do anything else because the scale of Celsius and Kelvin are the same. So 100 degrees Celsius, that would be what in Kelvin? 373. So to go from Celsius to Kelvin, just add 273. So what if I had 25 degrees Celsius? What would that be in Kelvin? 25 degrees Celsius remembers room temperature.
You gotta subtract it.
Not subtracted. If I'm going from Celsius to Kelvin, I'm adding. 298. Okay? I just add 273. So if you're given a Celsius value, and that's most of the math problems, is it gives you a math number in Celsius, you always got to remember, put yourself a note, always make sure that you convert your temperature to Kelvin before you do the math. And what I usually do is I figure out what each variable is. What is temperature 1? What is temperature 2? What is volume 1? What is volume 2? And then once I get it written out, then I just add 273 to any Celsius numbers. Then I can do the math. So the formula for this, because volume and temperature both change in the same direction, I have one over the other. So V1 divided by T1 is equal to V2 divided by T2. If volume goes up, temperature goes up. If volume goes down, temperature goes down. So that's why they are set up so they divide by each other to make them proportional. So let's practice this one, then I'll let you do one. So first, a sample of gas has a final, V1 over T1 is equal to V2 over T2. So Boyle's, remember, is pressure times volume is equal to pressure times volume. These are divided by. Okay, so let's read this problem. So a sample of gas has a final volume of 24 liters at 105 degrees Celsius. So if you see liters, you know liters is what? Volume. And you see degrees Celsius, you know that that is temperature, right? So if you see temperature and you see volume, then you know it's going to be Charles's law. Okay, so if I see volume and temperature, then I know I'm going to use Charles's law. So that means that I need V1 over T1 equals V2 over T2. And I need to know what is V1, what is T1, what is V2, what is T2. So a sample of gas has a final volume of 24 liters. So 24 liters is what? Is V2. Because it says final volume. So that's V2. And it has 24 liters at 105 degrees Celsius. So what is 105 degrees Celsius? So read the question. It's T2 because it's 24 liters at. So see how those are grouped together? So that means this is T2, is 105 degrees Celsius. So what was the initial volume? So my unknown is V1. So V1 is my question mark. What was the initial volume if the initial temperature is 25 degrees Celsius? So that would be T1, 25 degrees Celsius. Okay, so just like I did with Boyle's, I'm just going to identify what are the three I know, what's the one I need to find. Before I do any rearranging, before I go any further, the next step, you don't do with Boyle's law, the next step is this. Convert to Kelvin. right? And just remember, degrees Celsius plus 273 is going to give you Kelvin. Kelvin minus 273 would tell you degrees Celsius. So all you have to do is you have to either just add or subtract 273. Just depends on what your number value is. I've got to have Kelvin. And I look and I see it's Celsius, so I know that my number's not in Kelvin. So that means T1, I've got 2, add 273. T2, I've got to add 273. So 25, that's room temperature, 25 degrees Celsius, but plus 273 is 298. 105 degrees Celsius, just over boiling point of water, but add 273, so that is 378. Now I've got my numbers where they belong. I've got to have temperature in Kelvin, so just put yourself a note that that's one to always check with Charles's law. If you have temperature with the gas law, it's got to be in Kelvin. So next, I've got to find V1. So V1 over T1 is equal to V2 over T2. So how do I get V1 all by itself? If I multiply both sides, do you see times T1 times T1? Do you see if I multiply both sides times T1, T1 and T1 will cancel out on the left side of the equation. When I move it over to the other side, T1 was in the denominator. When I move it to the other side, it ends up in the numerator. Right, so that T1 is going to get multiplied times V2, and then I've got to divide it by T2. Just make sure that you use your Kelvin numbers. So 24 liters times 298 Kelvin divided by 378 Kelvin. So also you can kind of check if you keep your units, Kelvin and Kelvin cancel. It's going to leave your units in liters, which is your volume. 24 times 298 divided by 378. $18.92063492 liters. And when you go to do this rounding, you've got to go back to the measured numbers. So 24 liters, how many significant figures? 2. 105, 3. And then 25. So that means I've got to round to 2 significant figures. So the 1 and the 8, those are the first 2 significant figures from the left. Next number is a 9. So what'll that do? It's going to round it to 19. So just 2 significant figures in my answer, 19 liters. All right, try this one. So what is 12.5 liters? Volume 1. What is 15.5 degrees Celsius? T1. And then 89.5 degrees Celsius? T2. So what I want to find? V2. Good. Okay, so I wrote them out. Very next thing I do is convert them to Kelvin. So add 273 to 15.5, add 273 to 89.5. That's always like, remember, if you've got temperature, you've got to do that second. So then the next one, so if V2 is, I need that all by itself, what do I have to move? T2. So see if on the right side of the equation, V2, I've got to get T2 to the other side. So that means that I have to multiply both sides by T2 so that that will cancel. And that's going to move T2 into the denominator over on the other side. So V1, 12.5 times T2, which is 362.5 degrees Kelvin, divided by T1, 288.5 degrees Kelvin, and I got 15.70623,917 liters. Yes? Okay? If you didn't, just make sure you practice going back over these. And that's, it's not uncommon. Like I see that's almost always the reason that people lose points when they do these on the take-home test is because they just swap them. Okay? They put T1 where T2 should be. So that is why like listing out what is V1, what is T1, what is V2. It seems a little redundant at times, but doing it that way decreases the odds that you're going to mix them up just by plugging numbers in randomly. Okay? So last thing, how many significant figures should my answer have? Yay, good, right? Because 12.5 is 3 significant figures, 15.5, 3 significant figures, 89.5, 3 significant figures. So I'm going to keep the 15.7. Next is a 0, so what happens? Just all drops off, right? So 15.7 liters. Keep the decimal place. Okay, so there's a couple. We're not going to do Gay-Lussac's law. I think the Boyles and Charles is plenty, okay? Because that's another one with temperature. So this one, you don't have to worry because this one is, no, this one you don't have to worry about because this one's the one that has the pressure and temperature changes that occur. And so that's Gay-Lussac's. But there's this one. We will do this one next time just to practice. So you can do this one if a 52-liter cylinder of gas at 27.3 degrees Celsius is compressed. What's the final temperature? Because this is volume and temperature. So this is the Charles's law. So you can do this one. And I think I might have another one or two in there. So the relationship when we are talking about things that are gases, right? So when we have gas molecules, those molecules, remember, they don't really touch each other. So these molecules are like spread way out in this cloud. So they're moving around. They act independent of one another, but not so when we're talking about solids and liquids. So remember that solids are when you have molecules that are very, very close together, packed in extremely tight, touching one another in this nice kind of uniform, regular arrangement. Liquids, there's a little more room, but remember that just allows molecules to flow past each other. So that's why liquids can be poured. So they're still very close together. There's just a slight amount of space so that those molecules can slide. So when you do a change in state, going from solid to liquid, that's melting. Going from liquid to gas, that's boiling, right? But if you go from a gas to a liquid, that's called condensing. So condensation, when things become a liquid, so gas to liquid is condensation. And if you go from liquids to solids, that's freezing. So you can have freezing and melting, then you can also have boiling and condensing. Those are the more common. There are examples when solids go directly to gases. It doesn't happen all that often, but if you have, when my children were little, I had ice cube trays, like the plastic trays. So we'd have like 6 ice cube trays. I didn't have an ice maker. Like this is like the very first refrigerator or freezer I've ever had that has an ice maker in it. And it makes god awful noise. Like I wish that it's like in the middle of the night, you hear going, bang. And you're like, what was that? It's just the ice cube falling. I'm like, geez. So my freezer never made those kinds of noises. But my kids' friends would come over and they were like, our grandma has ice cube trays like that. They used to tease me all the time. But if you have an ice cube tray and you make ice and you leave it in there and you go off on vacation, you'll come back and it's like gone. Have you ever seen that? Like where the ice gets really, really thin, that's actually sublimation because some of the solid ice actually converts directly to a gas. And that's why your ice cubes actually shrink over time if you don't use them. But it doesn't happen all that much, but that's actually this side. So this is when solids and gases can convert to each other. But by and large, you have gases go to liquids, liquids go to solids, and then vice versa. Those are the much more common ones. But now when things are liquids and when things are solids, what determines their state has to do with these attractive forces. So attractive forces are when molecules are close together. If they are very attracted to each other, then they tend to be a liquid at room temperature. If there's low attraction, then they evaporate quickly because there's not much holding those liquids together. So we'll talk about a couple of them just because we'll probably cover the first two and we'll finish this next time. The weakest of all of the intermolecular forces. Intermolecular means forces between two molecules, okay? And you don't really see this with gases because gases, they don't touch each other. But when we're talking about solids and liquids, so this difference, why two gas molecules or two liquid molecules want to cling together or not, has to do with these intermolecular forces. The higher the force, the stronger the force, the higher the boiling point that a liquid will have. So the more the liquid is going to want to stay liquid at higher temperatures. The weakest one. So the weakest one, they call these London forces. So London forces, also sometimes called van der Waal forces, also sometimes called dispersion forces. So it really just depends on the book that you read. I like London forces. I'm fine with London forces, but dispersion forces are sometimes like they just randomly throw that word out there, so don't let that throw you. These are the forces that are the weakest of all five of them, and really you see these in nonpolar molecules. Nonpolar molecules, remember, are molecules where you have like carbon and hydrogen. So those hydrocarbons. So molecules like pentane, hexane, octane, like what you find in gasoline. So these molecules, here's how they describe their attractive forces. So because they're nonpolar, they're described as being very neutral. So the one that's kind of shown in this tanny kind of gray image. So the dots are the electrons that are going back and forth between carbons and hydrogen. So remember that carbon and hydrogen share their electrons equally. And so this creates a very neutral molecule. So neutral molecules, I told you, is sort of like plastic. It's not attracted to anything. So if you tried to stick it to something, it would just fall off. Neutral molecules have no charged nature at all. Those are your nonpolar molecules. But there are instances where electrons might be on one side of the molecule or the other side of the molecule, but it's like an instantaneous thing. So like if you look at those ones that are over on the right that show the blue and the red, do you see the top one where it looks like more of the electrons are around the top of the molecule? And that's just because those electrons are going back and forth, back and forth, back and forth. And so it's sometimes, maybe all the electrons went up instead of being like half and half. So that might make that top area a little more negative, but as soon as it forms, it disappears. So they give you the analogy, it's kind of like saran wrap. So saran wrap, my husband like despises saran wrap because no matter what he does, you pull the saran wrap, you tear it off, and what happens? Right? So one little piece goes bloop, and you're like, So you reach and try to square that one, and the other one goes bloop. Okay? That's kind of like London forces. They're very weak, but they do have this slight attraction that occurs. This is the only attraction that nonpolar molecules have. It's these London forces. So only nonpolar molecules, long chains of carbon, like pentane, hexane, cyclopentane, cyclooctane, all of those hydrocarbons that we talked about in chapter 4, this is the only kind of attraction that they have. And this is why when you spill gasoline, what does it do? Does it stay on the concrete? It evaporates, right? So it spills and then it evaporates, even though it's a pretty big molecule. Gasoline contains at least 8 carbons, which is really big compared to like sugar. Sugar's only 6 carbons and it's a solid at room temperature. But gasoline, because it's nothing but carbons and hydrogen, has very weak intermolecular forces, so those molecules evaporate quickly. So nonpolar molecules that are small, they're always gases because they really don't have any attraction. So things like CH4, that's methane, right? Natural gas. Even propane, right? Propane is in a cylinder. The only way you can liquefy it is by pressurizing it. So those are all exist at room temperature. They would be gases, and that's because these are such weak forces. They only have London forces. Try not to draw my S like a cursive S. Some people are like, what is that? Because they don't know what cursive is. So if you only see carbon and hydrogen, London forces are the strongest forces, and they're pretty weak. You got to have a pretty big hydrocarbon to have them be liquid at room temperature. Things like octane, hexane, decane, those are liquid at room temperature. If we add nitrogen, oxygen, fluorine, or chlorine, then we're going to have a polar molecule. And here, the attraction is very strong. So in this one, this one is showing a ether molecule. So it is a CH3 and a CH3, but those two CH3s are joined by an oxygen. So remember that oxygen is an electronegative atom. Nitrogen, oxygen, fluorine, and chlorine. If the molecule's small, but it has one of these, then remember it's going to create a permanent imbalance in the sharing. So the oxygen pulls the electrons towards it. That means that wherever the nitrogen, oxygen, fluorine, or chlorine is, that area always becomes more negative. So then this side becomes more negative. That means down at the bottom, this side down here becomes slightly positive. So now they start to line up. So the oxygens want to be around other CH3s. Slight positive want to get near slight negative. Like magnets, they attract. And do you see how it almost starts making layers? So the oxygen areas, oxygen ends up being more surrounded by CH3s. CH3s surrounded more by oxygens. This creates what they call a dipole-dipole. So think of dipole-dipole just means it's polar. Dipole-dipole has at least one nitrogen, oxygen, fluorine, or chlorine. This molecule is liquid at room temperature, even though it's only 2 carbons. Because it has the oxygen, this is a liquid at room temperature. And that is because these molecules want to hang out. These molecules are attracted to each other, so they want to stay together. So this is why it's a liquid at room temperature. It's the ones to remember though, nitrogen, oxygen, fluorine, and chlorine. If you only see one of those, then odds are it's a polar molecule. Okay, so I will quit there because the next one we want to talk about is hydrogen bonding, and that actually ends up going into like a discussion of hydrogen bonding and how water is sort of this unique thing. So I want to leave that to the next time. Okay, so between now and Sunday night, do the dynamic study modules for the gas laws. Did you get that figured out? Oh, did you try to do it on campus so that maybe you won't lose connection, or was that when you were on campus? Like you lose connection? Like, could you try it, like maybe like tomorrow, if you're on campus, try and connect with them and do a chat? Since I didn't know